Another approach that we can take to solving linear systems of equations is called Gaussian elimination. Now, Gaussian elimination is really just the substitution method, but shorthand. And way back, I mean, students have always kind of been interested in this, but not loved it. But they love it a whole lot less now because it requires doing arithmetic in your head, and many students struggle with the arithmetic. And then when I put in your head as part of that phrase, then that really makes it scary. Okay. But we're going to talk about it today and show you a little bit, kind of an introduction to matrices. When we talk about a matrix is just a rectangular array of numbers. Yeah, I can get that written. Rectangular array of numbers. It can have as many or as few columns and rows and columns that we need or want for our situation. And different authors, different people use different notations for writing their matrix, but I'm going to be with the square brackets. Square brackets, or sorry, a matrix can be as small as a single number. It could be a single row of numbers. It could be a single column of numbers. Okay. Or it could have multiple rows and columns. So maybe it looks like 2, 1, 3, 9 for the first row, -1, 0, 4, 2 for the second row. Notice how the numbers line up. We need to not make them willy-nilly, so there's some organization to our array. When we're talking about horizontal movement, so 2, 1, 3, 9, or -1, 0, 4, 2, these guys are rows. So the top row is what we'll call row 1, and the second one is row 2. When we're talking about up and down, and the organization here, okay, these are our columns. So this would be column 1, column 2, column 3, column 4 in this particular matrix. Now, if we had more time this semester, we would get to do some arithmetic with these and get a little deeper. But today, specifically, our matrices are going to have meaning. And that meaning is that they're going to represent our systems of equations. Okay, so remember, rows are horizontal, columns are vertical. When we're given a system of equations, then we start by creating what's called an augmented matrix. The augmented matrix has one row for each equation. So the equation x plus 2y equals 5 will take up a row, and we'll use another row to describe 3x minus y equals -6. When we create our augmented matrix, we just use the coefficients and the constants that are involved in the equation. So 1x plus 2y equals 5. We will just keep the 1, the 2, and the 5. So that means 3x minus y equals -6 would become the row of numbers 3, -1, -6. Now, if our matrix represents an augmented matrix represents a system of equations, okay, we will designate where that equal sign is. Here's our x's and our y's and our constants. Okay, so the reader knows that these are our coefficients of our variables, and these are our scalar or our constant values. Some authors will dot this line. I think our book is a solid line book, and that's what I'm going to draw when I do these on the board. Now, when we're working with our matrices, there's only certain things we're allowed to do. We have to be careful that we follow all the rules and we don't mess anything up. One of and those things that we're going to do are called row transformations. I do understand that we have the word row here, so that means those are our horizontal. we had the top row represents one equation and the bottom row represented the other in this example. Hoping if I do the dual page it won't make it too small. When we are working with our rows along the way, we can change places with any two rows that we want. The reason we're allowed to do that is because if I was looking at this system of equations here, when I copied it out of the book, if I wrote the bottom equation first and then the top equation second, and I wrote them in this order instead of that order, understand, hopefully it's clear that that wouldn't change what the solution set is of that system. Okay, so if I want to, when I move it, I have to move the entire row, but I could put the 3, -1, 6 in the top row and the 1, 2, 5 in the bottom row if I wanted to. And I would still have the same set of solutions to my system. Something else I'm allowed to do is multiply any row of a matrix by a non-zero constant. Multiplying by a non-zero constant means anything but 0. If I multiply this entire top row of numbers by 6, okay, that would be the same thing as multiplying both sides of this equation by 6. Okay, or similarly, if I wanted to take both sides of this equation by 12, I can multiply this entire row of numbers by 12. Again, none of that will change what the solutions for the system are. It will just change the way the equation looks. The third one is uses some vocabulary and some things that hopefully that'll become more clear as we start doing examples. But I can replace a row of the matrix, any row that I want to, with a linear combination of two other rows. A linear combination means I can add or subtract those rows. I can multiply them by 2 or 4 or 6 before I add or subtract those rows. And whatever I come up with, I can replace one of the rows with that value. So again, we'll practice some of those along the way. That one's a little more difficult to demonstrate until we just jump in to what we're doing. When we're doing Gaussian elimination, okay, what we're going to be doing, our first goal, our first job, our first step, is that we need to get a 1 in the first row in the first column. Let me see if I can drag and change places. Here. I think that worked. Look at that. Okay, so I need to get a 1 up here in the first row, first column. Okay, that step's already done for me if I look at this top thing. Okay, after that, I want to get zeros in the rest of column 1. I want to get zeros in the rest of column 1. Okay, that's going to be using the linear combination idea that I just mentioned. After that, we'll stair step down to the second row, second column. Okay, I want to get a 1 here. And we have to go in this order or we're going to screw things up along the way. If I started by getting a 1 here, then when I go to make zeros and 1s other places, it's going to mess up everything I've done. So 1 first, 0 next, 1 after that. If this was a bigger matrix, I would get zeros in the rest of row 2, and then I would continue to stair step down this diagonal until I either run into this bar right here, or I run out of rows to go down. So before we do that, and I'm going to erase this guy here to make room. If I was wanting to solve this system of equations, let me see if I can, copy and paste it in a special way right there. If I wanted to do elimination, we know that it's just as easy to eliminate the x's as the y's here. They would be the same number of preliminary steps. But when we're doing Gaussian elimination, we always start, we're always working from left to right, which means we are going to, eliminate the x's every time, no matter what. So here, if I wanted to eliminate the x's, I would multiply both sides of the top equation by -3. When I do that, I can't forget to take every term on both sides of that equation times negative 3. Put a line there. So then my next step would be, once these guys are opposites, I'm going to add them together. Then meaning the two equations, my x's are gone. It says negative 7y is equal to negative 21. I would do my one step now to solve for y and find out y equals 3. And then I would put it back into one of the top equations, which I'm going to pick the top one because I already have a 1x there. And I would find out x is negative 1. That's a 5. That's what it's supposed to be. Then I can write my solution set as an ordered pair. Because my video is getting long, we're going to start the next video solving this system using Gaussian elimination. So stay tuned and hop into the next video and we'll jump in from there.